We're going to cover a great deal of the highlights of quantum error correction. I completely rewrote my talk last night. You may notice the title had nothing to do with the original one in the program because I felt that the thing that we were lacking most in this forum was the error correction side of things. So after today, you should at least be aware of what quantum error correction looks like on a quantum computer, the kinds of things that cannot be done yet, and the volume of software that still needs to be written, which is why I'm here. I'm really hoping that some of you will send me an email at the end of this talk and be interested in learning more about how quantum error correction works. 1 hour will not turn you into an error correction expert. It will just give you a teaser and a taste. And participate in a course with me over a period of weeks and months until you can do the kinds of design automation tasks that we're going to describe in this talk. So, summary, hands up during the talk. Don't leave it to the end. Any questions? By all means, just shout them out. So, there are a lot of papers on quantum error correction. You could be forgiven for feeling that it was overwhelming and not reading any of them. And I'm sure that's the approach many people do take. A lot of the attention when it comes to quantum error correction comes to a paper I wrote over 11 years ago. So there is a 2012 paper on surface code quantum error correction. It is very dated, all right? It still becomes what people cite, what people read, but please note that there is a lot of research that is done that has thoroughly superseded in every conceivable way that work. We will touch on most of the highlights today. There's also Craig Gibney's work, so it's a very prolific research, one of the latest shining lights in quantum error correction, has made things very much better. He's one of my co-workers at Google, and the two of us put this together for you today. So where do we begin? So our goal is to explain quantum error correction in stages. Firstly, why it makes sense to make that the focus of your existence. Secondly, what we at Google are planning to do when it comes to realizing quantum error correction, what a large-scale quantum computer would actually look like, at least how we imagine it would look like at the moment. And then all of the theory that we can cram into 1 hour, and I'll try my best to convince you just how beautiful and interesting that field of research is and hopefully get you on board. So if you take away nothing else, there'll be these two papers. So modern quantum error correction is really in these two papers, not the 2012 paper. If you email me, I will give you a copy of my slides. You don't need to take notes, it would not be feasible. I'm going to go quick. And there is a package called STIM, which will be the beginning of the kinds of automated software that I would like to build together. So, Google, 214 authors and counting. So we are growing at approximately 50% a year. Read job opportunities. Get in touch if you care. So, do we really need QEC? Most of this conference, we have avoided the topic of quantum error correction. We've talked about an algorithm, we compile it down to gates, we run it on available hardware. Awesome. So do we really need it? At Google, we did some random circuit sampling. We showed recently that you could do something that you could not do even on Frontier. Fantastic, but it's not very useful. I mean, it's a particular class of random numbers, let's be honest here, okay? IBM. A great deal of respect for IBM, they do great work. A 60-qubit simulation, again, beyond brute force simulation, meaning if you took a state vector simulator, you wouldn't be able to do it. But within weeks, there were papers saying, hey, but I can do it this way, all right? And papers that said even if you ran that same problem on a 1,000-qubit computer, we'd still be able to do it efficiently classically. So my takeaway from these kinds of points is that if you really want it to be useful and beyond classical, it's going to have to be big. You should never forget that a quantum computer runs very slowly, all right? If you think about a single 64-bit addition on a modern computer, it takes less than a nanosecond. If you do the same thing on a quantum computer, even a fast superconducting quantum computer, it's going to take about 1/100th of a second. If you add up all the dollars it takes to build a quantum computer and turn those same dollars into classical hardware, you'll find there's easily 10 to 15 orders of magnitude difference in just wall clock speed. And you have to make all of that up with an exponential runtime algorithm, which you have to go to a fairly big problem size before you've got any chance of an advantage, right? So all that screams to me, you've got to do error correction. We're not talking about hundreds or thousands of gates. We're talking billions and trillions and quadrillions of quantum gates before you really get to the regime where you have a chance of doing something useful. You need a big, fast, error-corrected quantum computer. So how big? Well, fortunately, there are lots of very smart people that can take quantum mechanics, quantum computing, and turn it into algorithms that they, at least at this current point in time, think there is a chance of beating a classical computer on. So these are works both from Google and Microsoft. There are many others. I can't cite them all. It's really quite remarkable, if you think about it, that this is even possible. We're talking about 1 million qubits, which is about 1,000 logical qubits. That's 1,000 bits of information to describe your problem. This icon, which sits on my desktop, is 23 kilobytes, right? Think about that. This is 100 times bigger than the amount of data that you're assuming you can have available to describe your whole problem. Your output's going to be 1,000 bits. So, should we expect this number to come down? Probably not. It is actually quite likely, as people get smarter on the classical side of things and squeeze out the applications we think we can do, that this number could go up. Now, of course, we do research, I do research to try to push these numbers down, but I don't think you're going to wake up one day and say, oh, we only need 10,000 qubits. It's more likely we go to 10 million than we go to 10,000. So where are we currently? A very, very long way away from there. So this is a picture of our latest lab at Google. You will see that we have a cryogenic fridge. Base here is down at 10 millikelvin. You have racks of microwave electronics that deliver signals to the chip that sits at the base here. The chips live way, way down at the bottom of what looks like a Russian doll of cans. It's a fridge and a fridge and a fridge and a fridge. A whole bunch of wiring, and then there'll be the chip in here that actually does the work. The quantum chip itself does nothing without all the rest of it. If someone asks me what is a qubit is the 1 millimeter square patch of silicon here, plus its 4 wires, and the liter of electronics that then controls it. Qubits are not small, they're not microscopic, they're huge. So more specifically, we have an LC oscillator. So it's an oscillator with a fundamental mode, a first excited mode, and more excited modes. It's not technically a qubit, it's a multi-level system. You could in principle use it as a qubit, we don't. We focus on the lowest 2 levels. Any excitation above the first excited state is an error called leakage. These qubits have a tunable frequency, and in essence, we can tune the frequency such that we're either interacting or not interacting and do gates. That is all I'm going to say about the physics of the devices, except for their problems. So one of the things that we have is 2-level systems, which is a generic name for something we don't understand. What we do understand is that as you sweep the frequency across the range of tunability, there'll be certain frequencies where suddenly the coherence time is terrible. And this is, of course, a problem. It's particularly a problem because at 10 millikelvin, where you would think everything was frozen and solid, that on the timescale of minutes to hours, these move, and we don't know why. So you'll tune up your qubit saying, all right, it works well here, and then you look away for a few minutes and come back and you go, it doesn't work well at that frequency anymore, and you have to tune up your computer again. Now, if you have a small number of qubits, this is okay. Once you start having dozens of qubits, it becomes a very large software engineering problem to try to remember the frequencies where it worked out, remember the configurations where things worked out, and keep everything working consistently. In practice, this translates to when we want to do a flagship scale experiment, it takes a number of people hours to get it tuned up. It stays there for tens of minutes and then it doesn't stay there anymore. All right, this is one of the reasons we don't have a cloud service at the moment. It is too much work to keep these systems calibrated and working at their potential. You can keep them up and running terribly, right? Having multi% error gates, that's no problem. But if you want to get low error gates and good results, it requires hands-on expertise at this point in time, fiddling around with very complex software to get everything working nice, and then it doesn't stay there for very long. You also get hit by cosmic rays. It turns out that a square centimeter of silicon at a fraction of a degree above absolute zero kind of doesn't like it when it gets hit by a cosmic ray. And this would be fine if it happened every few years, but it happens every few tens of seconds. So when a cosmic ray hits a superconducting chip, that's operating at 10 millikelvin, it dumps so much energy on that chip that the entire chip stops working for tens of milliseconds. That is thousands of rounds of error correction. That is thoroughly unrecoverable. So, we're working on engineering solutions for this. This is an example of a correlated error that error correction has precisely zero hope of fixing. Which is to say, it takes a lot of work to build a quantum computer that has an error model that is correctable by error correction. So, it should no longer be thought that we do everything with error correction. A vast amount of the real error correction is done at the hardware level in the first place. The latest in terms of doing error correction is this experiment. So it's where we compare the error rate of a distance 3 logical qubit with a distance 5 logical qubit. And after years of effort and much work and an enormous amount of pain and money spent, we showed a 4% improvement while using a decoder that takes an exponential amount of time to run. And we didn't suppress leakage, so you'll see these kind of sweep up a little bit. So if you ran this for long enough, it would stop working. And you also have the problem of cosmic rays and the movement of TLSs. So, this is the effort of hundreds of people for years with hundreds of millions of dollars. It's really hard to build a real quantum computer. It should never be underestimated how hard this is to do. I will stress we feel we have a handle on each and every one of those problems, but each and every one of those problems will take more people, more time, more hundreds of millions of dollars to fix. This will not be done overnight. Now, the long-term vision and the next thing that we want to do is a long-lived qubit of order 1,000 physical qubits, where the error rate is down at the 1 part in a million level. So every round of error detection, the chance that you have a logical error is just 1 part in a million. Beyond that, we want to go to tileable modules and all the way up to this million qubit system. And just to really give a little bit more insight into what it means, what would a tileable module mean? So this is 10,000 qubits, where you've done the following thought exercise. You've had to think, all right, qubit needs amplifiers, needs wiring, needs control electronics, needs classical compute. Take all of that hardware and arrange it in a fan the same thickness as your patch of qubits. So we're assuming 10,000 qubits, 10 by 10 centimeters. Each qubit is a square millimeter. So that's your 4 inches aside. All the area, and then you sit there and say, well, if I need that much area of control electronics to talk to my qubits, it's going to have to be way out here. All right? I can't put it way in here. I can't put it on the fridge. It won't fit. Now, this assumes 10 times reduction in the current size of our control electrodes and 10 times increase in their power, because when you have coaxial cables that are this long, you lose about 90% of your energy. All right? So this is not infeasible. We believe it's doable. And it's just a picture and an example of the kinds of thought exercises I encourage people working on hardware to go through. Really think about what your system would look like at scale. What would modularity really look? Is it possible? Is there something that prevents you doing it? We will, of course, do research to try and make this picture better, but at least it seems possible. And then once you have a tileable module, you put 100 of them in a row. Yes?
Is that 10,000 qubits on one chip?
Yes.
Okay. Is that 1 million qubits on one chip?
No. So this would be 1 million qubits on 100 chips. So yeah, they would be edge to edge. So you might say, how can you do that? Already the chips that we use, we've done qubits on one chip and then bump bonded another chip where you have couplers. The couplers are really qubits themselves. We already do chip-to-chip coupling in some sense of the word. So you can easily imagine extending that to doing a good gate across 2 different chips. You just have to abut them in the right way. This also then would help with thermal expansion and other things. If you made a 10-meter long chip, which wouldn't be possible in the first place, but if you did, it would cause all sorts of other problems. So yeah, you can imagine along the spine of this fridge, which is now the Russian doll turned upside down, and you'd be lifting these things off with cranes. And again, this is not ridiculous. Fridges this size exist of substantially the same footprint, all right? So, people build some really big fridges. This is what a 1 million qubit system would look like. And again, the details will change. If you look at the current CAD drawings, which I apologize, I won't be sharing the current CAD drawings of what we're doing today, they don't look like this, but it's a thought exercise in making sure it's at least possible in principle. So, that's where we are, that's where we're going. Now let's talk about quantum error correction. So I am going to assume you all know quantum circuits. I think that's a very safe assumption in this forum. I'm also going to assume you're comfortable with Pauli matrices. Where you may or may not have thought is the next step, right? The Pauli matrices are a basis for arbitrary matrices, which means that we can have arbitrary noise on our qubit. Arbitrary, like anything, relaxation, anything. And then we can decompose that into this lovely linear sum, which means that it's just a linear sum of bit flips and phase flips. So that's the magic of quantum error correction. Arbitrary, continuous, random noise just looks like bit flips and phase flips. That's all you actually need to correct. And we can do that in a pretty straightforward manner. So here is a checkerboard pattern where one color, the white color, is designed to find the X errors. We have a bit flip error here, it's copied down onto this line and detected. That simple. All of these white squares do it in exactly the same way. If I have a bit flip error, it'll be detected here and here. I can use the endpoints of my chains of errors to locate my errors. So, you know, that's what you get. You get the endpoints of chains of errors. You then go in and you say, oh, great, oh, well, this would work. I'll match up these in pairs, or what's the nearest boundary. My errors must be there, do correction. But you immediately have a problem. This is already a small quantum error correction code, but it's a 49 qubit circuit. So how are you going to simulate that? Well, so one tool that we'd like to build on is STIM. It's open source, it was written by Craig Gidney, and it's very, very fast. It's very, very fast in the sense that, well, forget 49 qubits, this can do 20,000 qubits. All right, so distance 100, not distance 5, so multiply this picture by 20 in both dimensions, make it 100 rounds of error detection, and then it takes 15 seconds to analyze that circuit, and then it can sample from that at a rate of 1 kilohertz. So it's a very carefully engineered, impressive piece of software, again, written by Craig Gidney. It's what I would like to use the foundation for a whole bunch of more tools that we'll describe during this talk. But what does it really mean to use this? Okay, so I've said that you can use this, it's really quick, you can generate in a few minutes, lots of lines saying the error rate as a function of the physical error rate, but you know, what is the actual input to this? Well, to take it back a step, we're going to describe the input for just this piece of the circuit, because otherwise it gets too complicated to write on a slide. If you just focus on that rectangle piece of that circuit, it looks like this. So remember, white is detecting bit flip errors. I've touched the two corners, so here are the two corners that I've extracted from that rectangle. We're detecting bit flip errors, and that's all this circuit does. On the first, third, and fifth qubit, it detects bit flip errors over and over again. This is the repetition code. So you need to specify it in a .sim file, which is just a text file, which is very similar to many other ways of specifying a quantum circuit. We start off by resetting our qubits, apply errors. Do C naughts from the 0th to the first, from the second to the third, apply 2 qubit noise, and so on. You can also specify loops. And in practice, you would write a Python script, for example, that generates the STIM file for arbitrary code distance, number of rounds, and error rate. But that's still kind of painful. So here's the first design automation task. We do not have, but would very much like to have, and I would very much like to find people in this room that would like to build something like this, where you have a tool where you geometrically specify these numbers, this layout. You can imagine putting individual tiles, laying them out, and then it writes the Python script for you, all right, for an arbitrary distance. Something that can analyze the picture that you have in your head and say, okay, I get it. So this is distance 5, fine. I now understand what it would look like for arbitrary distance. Here is your input. That would be a whole lot more fun to work with than writing a Python script from scratch each time you want to analyze another code. In particular, and now I'm going to take a little bit of a segue. So that was design automation task number 1. Now let's talk a little bit about decoding. We're going to, again, keep it focused on this simple case of the repetition code. I'm going to use physical gates, so we don't have Hadamard gates, so to speak, on our device. We don't have C0 gates. What we do have is CZ gates and these Y-basis rotations. They do effectively the same thing. So this thing will take you from a 0 to an equal superposition of 0 and 1, and this will undo that, and they take the place of the Hadamards. And this is exactly the same circuit as that, just using gates that we actually care about. Why? Because the slides that I had were in that form, and that's what we're going to use. So the first question that we care about is, well, what data would we get if we ran this experiment? So let's put an arbitrary state, alpha all zeros plus beta all ones, in here, and assume there are no errors. What output will we get? Well, we should get all zeros, because there are no errors, right? Every single thing says, don't detect a bit flip, I'm done. If there is an error, it propagates to the measurements, and it hangs around. And what we see is then that change in number. So let's back it out and say, well, what if we got this arrangement of measurements? What would that imply in terms of where the errors are? So this is trying to get you to think as a decoder. You, the human, where would the error go, right? Have a guess. Where would it go? Well, here's one possibility. You could have two errors, one on the top line, one on the bottom line. That would explain that set of measurements. However, there's a better answer, and that's a single error here. And so your decoder is all about finding likely places of error that could reproduce those measurements. And this example illustrates the possibility that you could be wrong. All right? It could actually have been the case that there were indeed two X errors. Just because you pick the more likely version doesn't mean you're right. Right? So decoders will fail when the error density is too high. Please.
Could you have some kind of error masking at the beginning? Like, for example, on the left side of the X, maybe you had an error and then you had another error that is masking?
Yes. So, you know, it could in principle be the case that, for example, you had 2-bit flip errors here and they just cancel each other out. So yes, ultimately you don't truly know where the errors are. You just make a best guess of where you think they may be. And most of the time, that is good enough. Yeah. Most of the time, even if there were errors not where you think they will cancel out in the right way and they will preserve your information. So it's all about getting your ones back to zeros in a good enough way. Good enough technically, mathematically means your actual errors and the places where you think the errors, they form closed loops. That's why it's topological quantum error correction. Provided you're forming closed loops, everything's good. All right, so here's another one. Again, just think about where would the errors actually have been that generated that. You could have a two-error process that did this, but it's actually much more likely that you have a single error. So is there a general method? And the answer is yes, and STIM will do this for you. The general method is you look at every possible error on every gate in the system, and since each error leads in this picture to one or two detection events, you can associate them with the edges of a graph. So STIM will build that graph for you. And then once you have that graph and your data, you can convert your data into detection events. Anytime you have a change in measurement value, so here we went from 0 to 1, so we have a detection event here, we color that node of the graph. Here we went from 0 to 1, so this one is colored. Here we went from 1 to 0, so this one is colored. So we have a graph plus colored nodes, and then the game is to connect those nodes using the shortest possible length of string. So here's an example of doing that. We connect the top two and the bottom one to the boundary. You might ask yourself, well, why didn't we use physical corrections, right? Why didn't I actually go in and do the bit flip? But the answer is there's no reason to. Ultimately, once the quantum computer has done its thing and given you its output, you are working with classical information. You work out where the errors are, and then you fix the classical information. You do not need to actually go and change the quantum information. All you're going to do is track your belief of where the errors are, and then when you finally measure your data out, if, for example, I got a 0 here, I'd just flip the result. I'd say, well, actually, it's a 1. You know, I believe there's a bit flip error. I believe this is wrong, so my 0 is really 1, my 1's really 0, and you're done. So you never actually want to go back and fix the data. You just want to know what is wrong with the data. Now, we could have, you might say, said, well, this also involves two edges. Why didn't I pick this one? And the answer is because it's less likely. If you think about the error that has to occur to generate this diagonal line, it has to happen exactly here. So you don't just have edges, you have weighted edges. And these weights then allow you to intelligently choose the most likely explanation for the pattern of measurements you see. So here's a very quick overview of what classical processing looks. Again, we keep it simple, right? So we have a repetition code, we have a graph, time is passing, there's a detection event. What you do is you explore the graph around the detection event until you hit something interesting. In this case, the something interesting is the boundary, and then you match to it. And then time passes, you get more detection events, you explore around them, hit something interesting. In this case, it's each other, and so you match them. More detection events, more expansion, got to keep going, hit the boundary, done. And processing continues in this manner. The kinds of things I'm hoping you take away from this is that processing always stays pretty close to current time. There are more complex cases. This thing is called a blossom because it looks like a flower. I'm not going to go into the details, but essentially if the regions collide in a way that prevents further growth, you collect all of those regions into a single object and then keep growing around all of them at the same time. It's collapsed into a blossom. So this one keeps growing, hits something of interest at the boundary, and you rejig all of the nodes in the blossom. So, this is the thing that leads to the worst case complexity runtime of minimum perfect matching being poor, but this is rare, particularly in a quantum computer where most of your errors generate just a pair of detection events nearby, and the matching is very simple. Take your isolated pairs, match them together. It's actually, in practice, your average case is very, very quick. And it's low latency. In practice, of course, we don't work with repetition codes, we work with surface codes. It's a 3D graph, but it's in no way really different to the previous slides. Sure, it's 3D, but it's a graph. It has X errors and Z errors. They get detected. You have a three-dimensional graph now, but so what? The processing is still the same. All right, here's another thing that needs to be done. So again, 10 years ago, there was a method explained of how to do correlated correction. Correlated basically just means, well, here's my surface code that I know and love. When I have a Y error, it's an X error and a Z error, so I'm going to get not just one detection event, I'm going to get 3. But these are not independent. It's a single error that's led to 3 detection events. I could pretend they're independent and just say one's the X graph and one's the Z graph. I mean, that would work, but it's not ideal because the way things have occurred, we have a chain of Z errors that has led to a single detection event in the middle of the graph, which means I've got no way of knowing, should I match it to this side or this side? They're equally likely. However, because you know that this edge is correlated with this edge, after you've done this matching, you can go and tell this graph, hey, you know what? I just found a pair of detection events that were next to each other. That means it's very likely that you actually have an error on this edge. So you should weight this one a bit lower and choose it preferentially, and then you would match this way. And this helps. This helps a great deal. It means that you go from, if you think about it, a probability P of error, which is X, Y, or Z. Z error is either really a Z error or a Y error, so it's 2 of those 3 possibilities. You go from the probability of failure scaling as 2/3 to the number of edges to 1/3 to the number of edges, because every time one of your edges contains an error of the other type, you get a hint that it's there. And that makes things better. All right, so just let's recall, we wanted to automate this process of going from a code picture to Python scripts that generate that code for STIM. That's not user-friendly, but we could do better. What we'd rather do, instead of writing this, is just draw this, right? So you can see in this picture we have X checks, Z checks, and we've colored them differently. The same in this picture, the dark side corresponds to one type of check and the light the other. Wouldn't it be nice just to draw the 3D diagram in the first place and make that our way of coding? That's the next thing that we would like to automate. In particular, that frees you up to think about things in a more abstract manner, which you really want to do, because if you don't, you have to write code that generates things like this. So what is this? Right. We've taken some information, we've let it stay where it is for a certain amount of time, and then we've just moved it around. All right? So this is an identity gate, just a twisted identity gate. What you need to keep in mind is that when we try to detect errors, we also propagate errors. So that a circuit that touches its 4 nearest neighbor qubits, the last 2 qubits it touch will have correlated errors. So you need to be very careful which 2 you touch last. In particular, this type of check will propagate X errors to precisely these 2 qubits. And it's very important that you choose these 2, not these 2, because we have a logical X operator, meaning if I flip all of the bits along this, I flip the logical state of my data. If I allowed my measurement circuit to have an error that led to 2 errors along the parallel direction of this line, that would look like 2 errors to my code, and my code would only be able to correct half as many errors. I would have correlated errors that reduce the strength of my code. So you have to engineer the actual circuits in their order with great care to make sure you don't introduce those correlated errors. And in particular, as you turn the corner, you need to turn those circuits around, make sure they're still parallel and compatible. And writing a Python script to do this, I mean, again, it's not rocket science, but it's unpleasant, all right? And it would be much, much nicer if, again, you could just draw the 3D image and get a series of functions. One that gives you the Python script for this layer, one that gives it for this layer, one that gives you it for the terminal layer, one for this layer, right? That would be much, much more fun. And again, I hope that the process of building such a tool exists, but guess what? I'm a physicist, not a programmer. I do a lot of programming, but this is getting beyond me. And I'm here because I'm hoping for some of you, you go, you know what? Please explain to me the error correction and then let me build the tool, because that's my idea of fun, right? I want to find the people who look at that task and say, that's my idea of fun, sign me up. Here's some more fun. So we showed a twisted identity gate. Well, that's not the limit of what you can do. You can start with data here, propagate it along this merry path, send it back in time, all right, and then go with this. And I mentioned this very explicitly because I know there are people in the audience that have worked on quantum error correction level compilers where they've not exploited this, right? Where they're always interacting data just in constant time. You're allowed to go backwards, all right? This is equivalent to creating a bell pair and then doing a bell basis measurement. This is a teleportation experiment, all right? So as soon as you have a 2D, nearest neighbor piece of hardware, right, only has local interactions, but you whack the surface code on it, suddenly you have the ability to move information anywhere you're in a computer, including backwards in time, right? It's really cool. But again, do I want to write Python scripts for every layer of this? I do not. I'd rather have a tool where I just input the 3D structure and I get the Python scripts out and then I can put those into Sim. More. So we're now going to start talking about doing things. To date, we've only talked about identity gates, which is nice, but you don't do a whole lot within identity gates. The first and most easiest one is the logical Hadamard, where I just take all of my data qubits and just apply a physical Hadamard to them. That's enough to convert all my X checks to Z checks and vice versa, convert my logical Z to X and vice versa, and that is Hadamard. So you can draw that as just changing the colors of the boundaries. It also then changes the colors of the interior. And again, I'd like to be done and just have a tool that actually builds that. There is a much more complicated gate, which I won't go into any details besides presenting the link and the paper. This would be the topic of a whole hour lecture just on its own. But you can do a compact S gate. And again, actually doing that complex gate line by line right now is really painful. We would like it not to be. Here's another one which you probably haven't seen, all right, but is really, really important if you are writing a quantum error correction level compiler and optimizer. It turns out, just by changing the order of the gates, so just by changing the order of interactions here, you can get your patch of surface code to move. And with that primitive, you can do lots of cool things. I mentioned in the experiment that we had an issue with leakage accumulating. That comes down to the fact that you have data qubits that are not being measured, measure qubits that are. And the data qubits, because they're not being measured periodically, they accumulate leakage, right? You've got this multi-level system, and it just starts acquiring second and third level states, right? However, if you just change the order of the circuits and allow it to move, what you've also done is you've changed where the data qubits are and where the measurement qubits are. So now your data qubits get reset the next round. So you prevent the accumulative leakage essentially for free, just by changing the order of your circuit. So a really powerful technique. This wiggling is a way of removing leakage from your system. But you can do more. You can send your qubits on a merry dance. You can make them glide along. You can make them move diagonally. You can make them move horizontally. It means that you can pack your data completely densely. Right? No hallways, no space left for routing whatsoever. And a bit like those kinds of libraries which you may have seen, where you have shelf, 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 right next to each other, but they're on wheels. When you want to access a book, you just part the library, right? It's like parting the Dead Sea. You can just create the space you need to access when you want. So this is a really good way for reducing the overhead of quantum computation and sort of having just-in-time access to whichever piece of data you want. Now, we still haven't talked about anything other than single qubit logic. Let's start talking about 2-qubit logic. So here are a pair of qubits that we wish to interact. So you might say, well, okay, what's my CZ, what's my C0 gate? It doesn't work that way, all right? The primitives that you have are multi-qubit measurements of logical operators. So if you close up the gap between those 2 qubits, right, we create this bridge between them. By measuring all of the blue dotted objects, what I'm going to learn is the value of the logical Z operator. So I'm taking a logical parity measurement in the form of the product of all these local checks. The product of all the local checks equals these logical operators. So this is the 2-qubit gate that you have to work with. You can do ZZ parity measurements, you can do XX parity measurements, and you can use those to build C0 gates, both single control, single target C0 gates and single control multi-target C0 gates. And again, this is an example of the kinds of things you can do cheaply in quantum error correction that are just different to what you do when you have physical gates. Just because you have a physical C0 gate does not mean you have a cheap single control multi-target C0 gate. You don't, but you do in error correction. All right? You also have things like if I have a ladder of C0 gates, which when you have physical C0 gates, you might say, well, if I have n C0 gates, it takes n times more time. It doesn't in error correction. We just showed an identity gate that can bend backwards in time. Well, so too can the C0 gates, right? These things naturally can just be chained so that a temporal sequence of C0 gates actually takes constant time. Even more than that, I could take that big circuit, right? This great big long circuit of sequential C0 gates implemented in constant time, and then I could just tip it over flat. I mean, I can just manipulate it however I want, right? So it takes no time, like really no time. You can take any Clifford operation in general, any Clifford circuit, and make it take effectively 0 time by just putting it in the past, all right? You teleport it in, it's going to have some poorly byproduct operators, like those byproduct operators propagate through the Clifford circuit, no problem, you can do it. So that's your basic building block, multi-qubit measurements. These turn out to be really useful. So this circuit is state distillation. You take a qubit down here, and what we are effectively doing here is we're creating a logical bell pair. So here is one half, here is the other half of my logical bell pair. The other half of my logical bell pair I have encoded in a code that has a transversal T-gate. So to build that code, I need to use these single control multiple target C0 gates. You might say, aha, there was a slide just recently that showed us how to do that efficiently, but it gets better. It gets better because the state that is output from inputting a plus state, which is just 0 followed by a Hadamard, followed by this single control multiple target, is a very simple state. It's all zeros plus all ones. That's equivalent to a state that is stabilized by all x's, and that means we can just go and measure that operator. We don't need to do the C0 at all right? It means we can take our logical qubits, so let's imagine we have a U shape of logical qubits, up and then U back down, all right? Up and then U back down. If you trace through this, we skip 4, 1, 2, 3, 4, we then touch the next 7 around, there's one gap here, and then we do the rest, right? So this is an implementation of an 8-body logical X measurement that does the work of the single control multiple target operation, all right? And again, I say this to emphasize the extent to which once you turn on error correction, things are just not the same at the circuit level, all right? Circuit level is very technical, there's been some beautiful work presented at this conference, but as soon as you turn on error correction, and my assumption is you must, everything from the physical level and up, and all the compilation is completely different. So, with that in mind, your computation starts looking like this. This is assembly language, all right? Not the usual stuff used for where's my C0 gate, where's my Hadamard gate. That all goes away, and this is your assembly language. So these represent multi-qubit operator measurements, layer by layer. This represents an S-gate. This represents state injection, which we didn't talk about and won't talk about. There's only so much I can cover even at this pace. But it's essentially multiple attempts to put in a non-Clifford state, and there are space for 20 attempts, so the failure rate is 1 in a million. So that's what all of this is. This is what state injection looks like, and then after going through here, you measure out this second logical qubit. You use these measurements to detect whether you've had any errors. This code can detect up to 2 errors, so provided you haven't had 3 errors, you will detect the errors and discard it. It means that you get cubic suppression of error, so you can have T-gates of probability P of failure, and your output will have probability P cubed of failure. Your output lives here. So you need to get used to looking at this as software. You know, these are your fundamental operations. And of course, there's a lot of work to be done to automate this. These diagrams were created in SketchUp. If you've ever used SketchUp, it's a very simple 3D drawing program. But that is how the research was done. Not with some help from something else, it was done in SketchUp. You draw pictures in there, you look at the pictures, you ask yourself, what can I move in that picture to make it more compact? And then you move it, and you hope you don't break it, and you check it to the best of your ability, and sometimes you make mistakes. And then you go back and start again, all right? So all of these diagrams were drawn by hand, laboriously, all the research, you know, to get to a picture like this takes many pictures, because every time you deform it, you create a new file, you copy it, you get a second person, you do it in pairs. It's far from ideal. And it's obviously not where we want to be. And there is a lot of work. You know, every person in this room could send me an email and say, yes, let's get involved, and there's enough work for everyone, right? Ultimately, what does this mean? So this is the progress of research over time. This whole structure is designed to output a single T state. This one is more compact, that's here, and these are newer versions. This one down here can output a state for a Fowler gate in a single step, whereas in the past it might use as many as 7 of the pictures on the far left. This is, as in a single shot, does that. Also, this state can be used to output 2 T states. So again, details we'll have to wait for later, but these are pictures of real quantum error correction assembly language, okay? And we'd love to have ways to reduce that to things that went into STIM so we could simulate them. So, but we're still not done. So despite all that work laid out, I did mention that this was a qubit was 100 qubits wide and 10,000 qubits long. That means it doesn't look anything like this. This is a great big square of qubit. And that's not practical. It's not practical because if you think about a chip which has qubits on it that are superconducting, which means you have 3 to 4 wires per qubit, there's only so many wires you can get in from the edges before the interior becomes unreachable, which is why it's 100 by 10,000 qubits long, so that you can always reach the interior. We're going for a 2 by n array. Now, no one in this room at this point should be in any way confused. This is not 2 by n, right? This is a great big mess, and it needs to be recompiled, redone, preferably not by hand using SketchUp, so that it fits on our hardware. So yet another compilation problem that needs the talent in this room to work on it. Furthermore, you can do wonderful things like this. If you take any algorithm, you can write it as a layer of Clifford gates followed by a layer of non-Clifford gates, and just alternate those back and forth, all right? What that means is you can write it in this form. You do your layer of Clifford gates, and then your non-layer. And then you measure to see what your non-Clifford gates really were. They're always probabilistic. If you do a T-gate, 50-50, it rotates in the wrong direction. And then you have to patch in an S-gate, which fortunately, by the magic of quantum computing, you've already done. So you just choose whether you actually patched into the computation by the basis of measurement here. So this infrastructure will do the Clifford circuit, apply the T-gate, which is probabilistic, find out with the top measurement up there which way it rotated, and then based on that, either teleport in the corrective S-gate or not. And then send your data back in time for the next layer of Clifford gates, all right? So you can literally take any algorithm, and if you have enough qubits, spread out all of your Clifford gates at the beginning, do all of your non-Clifford gates in the next layer, and the only thing that limits the speed of quantum computation is how quickly you can perform a logical measurement, decode it, so that logical measurement has to get into a classical computer, has to be decoded, has to be reduced to a single number. Your random numbers, because after a while, keeping in mind we haven't corrected any of our quantum data, they accumulate errors. So the measurements, when they're first passed to the classical computer, they look like random numbers. You can't tell what it is. You have to decode it, bring all of those beliefs of where those errors were up to date, and then and only then do you know what that measurement is. Once that's done, you need to tell your quantum computer either perform some single qubit rotations or not, to choose whether you do a Z basis or X basis measurement, and then you can repeat the magic. So the clock rate of a quantum computer, an error-created quantum computer, is the sum of its physical measurement time, its decoder latency, and the time it takes to feed back that information to do a single qubit rotation. That's the clock rate of a quantum computer. It doesn't depend in any way on anything else. So in principle, it means that if your system has fast measurement and fast classical processing, it can run as fast as any technology. It doesn't matter what the underlying gate speeds are. If you have neutral atoms and you know how to do fast measurement, you're good. If you have ion traps and the gate's 1,000 times longer, but you have fast measurement, you're good, all right? It's only those things that determine how quick your quantum computer goes and how many qubits you have. And I stress, it's a lot of qubits to lay out an algorithm like this. We're not going to be able to do this for a very, very long time. But we can speculate. So here's a paper on factoring a 2048-bit RSA integer. And you'll notice that it's an adder, and it looks awfully flat. All right, this is using the exact trick that we talked about on the previous page. And again, this is done in SketchUp, by hand, laboriously, right? You can imagine that we're already pushing very hard the limits of what can be done using the tools we currently have. We need the people in this room to help us build better tools so we can do better research to get low overhead structures and better algorithms and implementations, right? We're really pushing hard up against the limit of the automation now, not in 10 years, not in 5 years, right now. We would be able to come up with better ideas to do lower overhead quantum computation if we had better tools for automating the work we do day to day as researchers. So, what to summarize? So, I hope I've convinced you that several things are true. One, we are actually going to need quantum error correction. Two, as soon as you accept that and get on with using it, it changes everything. Right? The computer doesn't look anything like it used to when you were mapping actual gates to actual physical qubits. You have a whole bunch of superpowers, putting data in the past, long-range interactions that you didn't have in the physical hardware, single control multiple target gates, multi-qubit operators. You have a lot of tools that you just didn't have at the physical level. And the optimization problem is completely unrelated to what it was beforehand. You're not breaking it down to the physical gates and optimizing those at all anymore. You're only optimizing down to the error-corrected structures. The physical gates are always just doing error detection circuits, always, over and over again. That's very useful at the hardware level because now that you know what you're implementing in hardware, always the same circuit, you can tune up for just those gates, just that repetitive circuit. And that is really quite a powerful thing in terms of allowing you to achieve higher gate fidelities because you don't need all these random error angle rotations. You don't need them at all. You just have to tune up one good gate, have it repeat, and it helps a great deal. So the goal is really to get people reading these, but I can summarize that even further. The summary is email me, all right? If you do one thing out of this whole talk, it's note that email address and just send me an email saying hi, all right? The reason being is it's really high time, well past time, that we got busy writing these tools to automate this research so that we can all as a community do better. This is not far in the future research. We have needed it for years, okay? So if you send me an email, the following will happen. We will go and teach you all of this properly, all right? This is not something you can learn in 1 hour. It's not something you can learn in 10 hours. We'll take the next 3 months. We'll organize a seminar series. We'll get everyone online and you'll learn it properly, all right? And then the next thing that will happen is we'll work together. We'll build an open source tool. You can all publish your individual contributions to it and we can all help this field move forward. And if that sounds like fun to you, send me an email. Thank you.